So first of all, to begin, the slides, this slide deck is at ls.st/rpg. So if you're having difficulty seeing what's being projected here from afar, go there, and there should be PDFs of the slides. So what I'm going to do is I'll continue with the same theme that George started, which is real-time astronomy. I purposefully selected a somewhat in-your-face title. Gone in 60 Seconds is a famously bad and terrible movie. I think if we don't do some of the software right unless we resolve some of the classification problems that George has been talking about, the story of real-time astronomy in the LSST era may be equally bad, because we really will depend on a lot of automated classification and automated everything from decision making to follow-up. So here's the context for this talk. The last decade has really seen a tremendous rise in the importance of time domain astronomy. And we have found new things from different types of supernovae, different types of explosive events, new kinds of objects in the solar system, objects outside of the solar system passing through the solar system, etc. All of these are elements that fall under this category. The timescales on which all these phenomena occur make them fleeting. So you either observe it while you can, or it's gone. So we have to study them before they're gone. And this brings to astronomy a whole new set of challenges, from real-time classifications that George has talked about, but also to really just systemic challenges of how do we build systems that can process this level of these levels of data points that are flowing through them, to actually down select to the one that's probably interesting to be followed up in any given night on any given telescope, and to then actually do the follow-up. So what I'm going to be focusing on in this talk is that aspect. It's how do we build those systems? Where are we now? Where are we going? What are we going to need to build? George has talked already about classification. We take the two talks together, and I hope you'll get a good feel for where we are as a community today and what are the challenges and where we need to go. So the challenge of real-time astronomy in a nutshell, or I guess in a few slides. First, you have the survey. And here I have the LSST, but you can, instead of LSST, you can put down any big survey telescope, even the ones that are operating today, like ZTF. The survey scans the sky, and the survey discovers interesting things that change. So here's an example from I think PTF. This is a supernova in a galaxy. And these are the kinds of things that we're interested in. Now, of course, we classify them. We used to classify them by hand, and now we'll have to do it automatically. And when we classify them, we need to watch out for objects that are not astrophysical. I talked about this yesterday, that there's a lot of junk in those images, especially in difference images. And we need to be careful not to be following up those. So we have a challenge of classification, both real bogus classification and of classification of physically what the transients are. Once we do that kind of thing, we want to alert the community to something interesting in the sky and follow it up. So study it, and study it in some cases quickly. And here's an example of a transient caught with PTF from a paper by Yikao in 2016 that shows this follow-up and study from discovery, that down there is 0 hours, all the way to 12 hours after the discovery. And by that time, there were all these observations from all these different observatories that were done on this object. So if you like exciting lines of work, this is one of them. You might get an alert and then forget about all your plans for the next 12 hours. This is what you're doing. It's worth it because you find interesting things. You find things like EM counterparts to gamma ray bursts. You find things like tidal disruption events, stars spiraling into black holes. You find things like, you discover things like superluminous supernovae, something that's even more super than a supernova. You find even more interesting things. This here is the famous binary neutron star merger that was alerted on by LIGO. This here is probably my favorite plot in the past decade, because the reason why is it shows how powerful a non-detection is. Because one of the LIGO detectors did not detect this signal. That's what basically these two halves means. It managed to localize where the potential object is, because it was in the only area of the sky that the detector effectively couldn't see. So non-detections are powerful. And closer to home, you find things like this. You find everything from interstellar visitors. We just had the first identified interstellar object passing through the solar system, Oumuamua. If you believe Avi from Harvard, it might be a solar sail from a distant civilization, extraterrestrial civilization. I'm not sure I buy that. And you find potential killer asteroids. Anyone here from Russia? I feel that universe has something against Russia. Because every time there's something crashing into Earth, it hits Russia. In 1908, there was this big Tunguska event that I think kind of opened the eyes of the modern world to the potential of asteroids actually hitting the Earth. And this is in 2013, one smaller object entering the atmosphere over Chelyabinsk, sending about 1,500 people to hospital because of glass cuts, smashing I don't know how many windows, et cetera, et cetera, et cetera. But these are the kinds of objects that we'd like to discover, hopefully, before they hit. And then there are objects like this, which is a weird star that's been discovered by Kepler, sometimes called Tabby's star, and where there was also an extraterrestrial explanation proposed for its variability, namely that it has a Dyson sphere around it, or a Dyson swarm. Okay, so these are the kinds of things that we can discover by looking at the time domain. Where are we today? So there are many surveys that are already active, and this is a plot that I really like. I got it from Eric Belm, who's a project scientist on ZTF. Now the survey scientist is ZTF. I'm not sure where he got it, but it gives you an idea of the surveys that have started operating back in the 90s and going all the way out to 2020s, and the kind of let's say, genetic relationship between the surveys, or how different teams kind of moved on from one survey to another. So you have surveys that were really pioneers, like Palomar Quest, and then went on to LaSila Quest, then CRTS, or CRTS2, then PTF, IPTF, now ZTF, and you have down there SDSS, moving on to LSST, BlackGem, and other surveys that are going to go in the 2020s. The thing that is common here is the increase in the event rate. So in the 90s, we're talking about few objects. Going out to the 2020s, we're going to be talking about millions of objects. So how are these events reported today? There's a wide variety of ways. Starts anything from private databases and scripts. So somebody has a database usually exposed through some website. Mailing lists. Sometimes you get alerts through mailing lists. There's something called the Astronomer's Telegram. It's also a mailing list and a website. There are a little bit more sophisticated networks. There's via EventNet that George mentioned. And the ordering that I have them in here is from kind of more manual, target and science specific, towards more automated and more general purpose. And that ordering also follows the scale. So these that are on top are on order of a few objects per night. These that are on bottom on orders of 1,000 objects per night. So this is kind of where we are, or I should probably say where we were until about 6 months ago. Where are we going? So I mentioned LSST yesterday and the day before. this is really the big driver of change here. So LSST will be delivering 10 to the 6, so roughly 10 million time-domain events per night. So the way LSST defines a time-domain event, it's anything that changes in the sky, whether it's moved or whether it's changed brightness. So it includes everything from actual extragalactic transients to variable stars to moving objects like asteroids and potentially even fast stars. So the reason why LSST thinks about it that way is because it's a general purpose mission, right? So somebody's junk is somebody else's gold. The famous example here are asteroids. Who here is an asteroid astronomer? Really? I'm the only one? We hate galaxies because, asteroid comes over a galaxy and you lose it. Who here is a galactic astronomer or galaxy astronomer? Right? Oh, Jesus. So galaxy folks infamously call asteroids the vermin of the sky because an asteroid comes over a galaxy and there's all kinds of confusion there. You think you found a supernova or whatever. But LSST is designed to try to serve as many communities as possible. So we don't want to do processing or retain some data that would make it impossible for galactic astronomers to find for the extragalactic astronomers to find supernovae and for asteroid astronomers to find asteroids. So that's why we send everything out. That's going to be a theme later. LSST has 3 processing modes. You can think of these as 3 different timescales. And here I'm going to be talking about the first one, prompt processing. So this is where every night we take the observations taken in that night. Actually, it happens in real time. As an observation is taken, process the observation, detect everything that's on the images, detect everything that's changed, and send out the alerts. When we do that, when we send out the alerts, this will touch upon something that George mentioned. We're trying to learn from experience from previous surveys and from our experience in previous surveys, and understand what is it in the alerts that has previously been missing that we could actually supply to make that classification easier. So in LSST's case, when we say an alert, it's not just a notification that there's a new object at this point in the sky. It's this whole list of things. So it's a notification that there is a new object in this part of the sky, but also it's photometry, it's astrometry, it's shape characterization, actually a few measures of photometry and a few different measures of astrometry and a few different measures of shape characterization. We attach postage stamps or little cutouts, little images of the object with each alert. So if you want to run some fancy convolutional neural net classifier on it, you actually have the image that you don't even need to rely on the features. We do send out features. We do compute the features on that object. And in a time series of its previous observations, because we look whether we've seen the object at the same point in time previously, so we'll give you that as well, and context, so temporal and spatial. What was there before? What is around that object? And I'll talk about that a little bit more in a second. The goal here is to make LSST a discovery machine and to quickly take any information that LSST has and throw it out there so that your algorithm on the other end could grab it, could decide whether it's interesting for your use case, could apply all the machine learning techniques that you're going to be learning about in the school, and ultimately decide whether you want to follow it up or not. How does this happen? This is just a brief sort of detour into the land of diagrams and pipelines. An image gets taken on LSST. In 2 seconds, it gets read out from the camera, which I always kind of find impressive. It's a 3.2 gigapixel camera, and it gets read out in 2 seconds, and it has practically no read noise. In about 4 seconds, that image gets sent from Chile to the US for processing. And then the first thing that's done is what's called single frame processing. So we take the image, we do instrumental signature removal, everything that I talked about yesterday in the first part of the talk, estimate the PSF, measure or compute an astrometric solution, then calibrate the photometry of the image. And we pass that on to image differencing. We difference that image against a deeper template. The reason why we've chosen to do that is because LSST will actually spend a lot of time observing in areas of the sky that are very crowded. So either places like the galactic plane, or places like globular clusters, or places like galaxies, external galaxies that are very well resolved. And it becomes difficult to find variability of point sources on top of such crowded fields. It turns out that it's actually easier to do that in image differences than in direct imaging, and it's more cleaner to do it in image differencing than in direct imaging, even though we have all those problems with false positives that we talked about yesterday. It's a tough one. It's really a matter of trading one thing off of another. So, but once we do that, we find all the objects that have changed. So here are two examples. New image, reference image, thing that's changed. For that object, we measure its properties. We go look into the databases whether there was anything there at that position before, collect all that information. We look in the databases about what's around this object. So in this case, we would say, this is around it, this is around it, this is around it. There's some nebulosity around it. We collect that information as well. And then we package all of that up into an alert. And I'll say in a second what an alert is. But the point is, everything we know about that object and about that little patch in the sky ends up being packaged into an alert and then sent out to you. Now, before I show you what happens with alerts, let me show you how this looks like in time, because I think this is really neat. It gives you a feeling for the complexity of some of these pipelines. So up here is time, goes from 0 to 140 seconds. And here, we take the first part of the LSST visit. LSST images are actually, right now, the plan is to take them not in a single 30-second exposure, but in two 15-second exposures, and then add the two exposures together. So we start with the first 15-second exposure. And while that's going on, we have a piece of software that's computing where all the known asteroids are. We read out the first exposure. We transmit that exposure to NCSA. We transmit it from the summit to La Serena, to where the first data center is. Then we transmit it to NCSA, which is from South America all the way to the US. And it happens in a couple of seconds. Then we take another visit, another snap of the visit. So that's a second 15-second exposure. So now we have two 15-second exposures. We repeat everything. And when we say in LSST that we're going to try to do this processing in 60 seconds, this is where a 60-second timer starts. So when the shutter closes in that second exposure, so now all of that gets sent to the data center. Then image differencing takes for about 15 to 20 seconds. Then we associate everything new that's been discovered with something that was with all the things that were previously known in the catalog. Some QA, SDQA stands for Science Data Quality Assessment. Those are automated QA metrics that get run on the image. For example, if you're observing in an extragalactic field and you discover that your image is phenomenally crowded, it's probably a problem, not a real thing. We generate all the alerts, it's packaging everything up. And at that point, we send it out to the community. Now, the telescope is not waiting for us to do all of that. And by the time we're there, the telescope has already taken the next image, because the telescope goes from one field to another in something like 5 seconds. So then we have a problem, because this takes longer. Well, thankfully, we can buy more computers. So we have another pipeline that's running in parallel and ready to process the next image, and so on and so on. So these are the kinds of things that you worry when you're building systems like this, and there's something similar that's done for ZTF as well. And another challenge here is that the machine, the telescope, is down there in Chile, and the processing is at NCSA. So when we say that we transmit that image, it basically means we take about 8 gigabytes of data, and in about 3 seconds moved from South America to Chile, which is kind of cool. It's amazing, by the way, how networks have become cheaper. When this was being planned in 2010, or this was planned in mid-2000s, it was almost impossible to do something like this. The whole plan was to do all the processing in Chile. Due to the development of the internet and streaming, and everybody wants to watch Netflix and so on, the bandwidths have grown so much that it became feasible to just buy the bandwidth and just send everything upstream. So it's pretty amazing what you can do when you're kind of piggybacking on what the technology and the world are doing. And I'll get back to that in a second as well. Okay. So now we have our 10 million detections. It's 10 to the 7. I just realized I have a systematic error in every single of my slides. Now we have our 10 million detections at the data center. And what do we do now? So how do we get that to you? Or what do we do first before we get that to you? Well, we first put those 10 million detections in context. So I mentioned already, I think I already showed you this slide. But this is now with a little bit more information. What is that context that I mentioned previously? So for each new detection that we find in an image, we go back into the database and dig out every single observation in that location in the past 12 months. We take all those observations, we put them on a pile. We add them here. That's this. So basically, we give you a year's worth of time series of everything that this object has been doing, if there was anything there. So if you're interested in supernovae, and your object has 12 years of data showing that it's varying, it's probably not a supernova. If you're interested in variable stars, that's your object. We also compute some features on those time series. We do the cutouts, and we also find objects in the data release survey that are around it. So is there a galaxy near that object? If this object is on top of a galaxy and it hasn't been seen before, then it's likelihood that it's a supernova goes up significantly. So that's the kind of thing that contextual information allows you to do. So all of that gets packaged up. So good. So now we have that. Now we need to get them out. And so this is where I think things become different than what you were used to, because most of us are used to right now accessing databases and accessing catalogs, running queries against catalogs. This is not a catalog. This is a stream. So what that means is, although I keep saying 10 million objects per night, it's not like at the end of the night you're going to get a table or a file with 10 million objects. Every 40 seconds you're going to get 10,000. Actually, every 40 seconds, in a burst of about 5 seconds, you're going to get 10,000. So if you really want to respond to these objects at a time scale of a couple of hours, then you need to be able to attach to the stream and to process the stream in a way that you'll find useful. So the stream is going to have all subtraction candidates. That means that we're not even going to cut on things like real bogus. So real bogus is an estimate on whether the object is real or not, or whether the object is an artifact. Why wouldn't we make a strong cut on real bogus? Because, if you care about really going after objects that are 99% real, then getting a factor of 2 or 3 more objects that are definitely not seems like a waste, which it is. But wait until next slide. However, if you have algorithms that can dig into noise and that can deal with, say, 50% impurities in the data streams and can actually recover interesting data out of that, then putting a high cut on something like real bogus would actually completely destroy your science case. And the example there are discoveries of very faint asteroids. So if you have a very faint asteroid that, sometimes you see it, sometimes you don't, or it's barely at the 5 sigma limit, it's going to be the likelihood of something at the 5 sigma limit being a faint asteroid or being just a false positive is going to be roughly 1 to 1, so 50%. But a faint asteroid is going to move in a very specific way. If you take 3 or 4 observations of an asteroid period, you can fit a Keplerian orbit to it. And you can easily, as soon as you fit a Keplerian orbit to something that has 4 or 5 observations, you know it's real, because the likelihood of having false positives that match a Keplerian orbit is essentially 0. So you have a very strong filter, very strong additional information or additional prior that allows you to take a very noisy stream and extract information out of it. So that's the reason why these streams are going to be big and why these streams are going to have essentially everything in them, even junk, because sometimes you can dig out very interesting signals out of that junk. And if you don't care about those signals, what you're going to do is you're going to set a filter that says, please do not send me all the junk. I'm going to say real bogus greater than 0.99, and I have objects that are almost all real. So this is how that is likely to look. I have about 10,000 sources per visit. Alerts get generated. They get put into an alert queue, and then we have full streams that get sent to external, what are called brokers. I'll say in a bit what that is. And we have something that are called user filters. And this is where you declare what is it that you're interested in. Are you interested in a very pure stream? You can say that here, and that only that is going to be sent to your client. Are you interested in a stream that, say, only has very blue objects because you care about quasars? You can send that here, et cetera, et cetera. The nomenclature is that if you're thinking about what we're doing today, we have data sets that are in databases. Our data sets turn into stream, and our databases turn into event brokers. So event brokers are places where you'll be able to essentially run queries on streams. And so the challenge here is that we have about 10,000 new objects every 40 seconds or so that we need to transmit, so 10 million per night. And how do we actually send that out? So if you look at the data rates, that turns into a few hundred gigabytes per night of data. And this is just raw information. This is the actual information content that's in the alert. So we looked at the technologies that exist for sending streams out. This is my slide from 2013 from IVOA Interop meeting. There's a really good, actually, standard from IVOA called Via Event that describes how you're going to package information into an XML packet. Just to get a feel for the audience, how many of you have heard or used XML? All right, I feel for you. XML is a format that's designed to, XML is a meta format. It basically allows you to express any format as XML. The downside is that it's fairly verbose. So in this example, to send 40 bytes of information in XML, I needed 787 bytes of actual text in XML. So that means if I have to send 300 gigabytes of information, I would have to be sending terabytes of information out if we try to encode it in this format. So this is one of the things that we were worried about at the time. And I said, overheads of over 10 to 20% are probably unsupportable. Now, the other thing that is challenging when you're trying to send 10 million alerts to people is that, moving that data from me to you may sound like a trivial thing. but doing it robustly is anything but. So we need to move 10,000 alerts in 5 seconds to hundreds of endpoints, so hundreds of people. So one issue that you have is throughput. That means just get that much data out of the data center and out of the computing system. You cannot push that much data out of a single computer, which means you have to have a cluster of computers. Once you have a cluster of computers, you have a fun distributed programming challenge of how you actually do that reliably and what happens if any computer fails. So that becomes difficult. And then reliability is another issue because whenever you have, again, a distributed system, you can have a server failure and your system has to be robust to that. We're used to writing programs and thinking that the computer will just execute it. When you get to these scales, that assumption is, or the computer will execute it without crashing or without anything bad happening to the computer in the meantime. When you move to distributed systems or to these scales, that assumption is just wrong. So basically, you have to start writing your code with the assumption that one of your thousands of computers is going to go down at any point in time, and that your code needs to continue working, or needs to find which computer went down, reallocate that workload to some other computer, and just continue working. So that's hard. So that's a server-side issue. On the client side, you may be attached to the LSST stream. I don't know, from an airplane, and you're passing over an area where there is no coverage, you get disconnected. What happens then? Well, we could say, tough luck, you've just lost all the alerts, but that's not polite. So we'd like to be able somehow for the user to be able to reconnect and say, hey, I'm back. Can I get all my alerts that I just missed because GoGo has terrible coverage over most of the US? That's for GoGo. So existing state-of-the-art here is that what we've been using in astronomy is based on 2 protocols. One is called XMPP. Those of you who still remember instant messaging like AOL and Jabber and all those things that seem to have gone away, that's the protocol that all those tools are using. And the second is a draft astronomy-specific protocol called VTP. And neither of those address throughput or fault tolerance. So this is what I'm demonstrating here. I spent 2 minutes on this slide, is that when you increase the scale, as the scale grows, something that seemed very simple before suddenly starts being complicated if you're trying to do it right. And the final problem is that we would like to enable filtering of millions of alerts and potentially dozens of alert streams. So filtering means, give me all the alerts that where the object sits on top of a galaxy, and write that in some query language. But LSST is not going to be the only survey out there. There are going to be more of them. What you would optimally like to do is something like in databases when you have 2 tables or 3 tables and you join the 3 tables, and you have all the information from those streams. So you have a stream coming from LSST, you have a stream coming from ZTF2 or LIGO, and suddenly you see that LIGO and LSST have triggered at the same time on an object that, with the error ellipses that overlap and those kinds of things. So we need that ability to fuse the streams and to filter the alert streams. And here's an example of what I mean by filter. So here's a very simple example. You have a full stream in. You could say, real bogus, is it greater than 0.4? So 60% chance, well, depending on how you scale it. If it's not, it's junk. If yes, continue. Does it have a quiescent counterpart? So did it change before or not? Does it have a counterpart in the static catalog? If yes, it's probably a star or a quasar. So if you're a stellar person or someone interested in quasars, that's where you're happy. If no, it continues on. Does it have 2 detections 30 minutes apart that are nearby? If it doesn't, then it's possibly a moving object. This is where I start caring. If it does, then you go this way. Does it have an upper limit from previous night? If it doesn't, then if it doesn't, then it's an older transient, so it was detected before. If yes, then it's possibly a young transient. And what you're getting out here is a stream now of filtered young transients. So you started with a full stream, it goes through this, and out comes a filter stream. So these are the kinds of things that we want to enable, and we want to enable you to actually write these queries on the stream for exactly the thing that you want to do. So how do we do all of this? This is by far my favorite cartoon. Let's not reinvent the wheel. We in astronomy are very much guilty of this too many times, that we kind of don't pay as much attention probably as we should to what's going on, especially in the industry. And we try to develop homegrown solutions or alternatives to things that there are others with way more resources and motivation than, well, resources mostly, than we have who are working on the same problem. So there are billions, literally billions of events flowing through compute systems each day of companies like Google, Facebook, Amazon, and Microsoft. And they need to serialize them, they need to transmit them, they need to have different streams fused, they need to classify the results, they need to act upon results. So it's things like whether our machines are up, are our machines under attack, where is the attack coming from, how are we going to react to it? All of that is happening today. And if you look at those problems, or look at our problems, you realize that basically the mapping is one-to-one. It's just that the objects are slightly different. So we were very lucky at UW that we actually had a person come work with us, Maria Patterson, who spent some time thinking about these things in the industry. And she basically looked at our plans and said, you know, you guys are these guys on this plot. You shouldn't be doing that because there are all these systems out there that actually do everything that we need. And so we settled on 3 solutions. One is called Apache Kafka. It's a streaming system that has been developed by LinkedIn. I'll mention it in a second. It's basically the thing that transports alerts around, things that move things around. It's like the internet equivalent of a truck to move things around. Data formatting, Apache Avro. So that would be, instead of writing packages in XML, there's a more compact way to store them, and it's standard and it's being broadly used. And for filtering and processing, something called Apache Spark. The downside of knowing all these things is that you become really attractive to people who have way more money than academics do. So Maria left for a startup about a month ago, and we're very sorry for that. So here's what Apache Kafka is. It's a streaming messaging, it's a distributed log system / messaging queue. What that, in essence, means is that it's a system that can reliably write messages from 0, first message, second message, and so on and so on. So I just keep adding to this queue. It supports as many writers into this queue as needed, and it guarantees that no matter what happens, the message will be written. So you run this on a system of 20 computers, 10 of them fail, the message will still be written. It has these kinds of guarantees. It's built to do that. That it also allows you to read. It also allows you to have a number of what it's called consumers. These would be people reading off the stream. And it remembers what is the last message that each consumer read. And it also guarantees that each consumer will see each message at least once. So if you're trying to read this, you know that you haven't missed anything. So no fear of missing out. And it's being used, this has been developed by LinkedIn. Now it's being used in Microsoft, Netflix, and so on. So every time you pay to Netflix to watch movies, you are subsidizing astronomy. So feel good about yourself. Data formatting uses something called Apache Avro. I'm not going to go into much detail about this, but it's a way to write information to write these packages that encodes what is the contents of the package, but essentially has 0 overhead. Because the schema is specified in very, very few bytes, and actually as a pointer. So relative to XML, Avro is, in essence, how much information you have, that's how many bytes are on the wire. So we like it very much for that reason. And then Apache is a system that I bet you're going to hear a lot about over the next 5 to 10 years. It was developed at Berkeley initially, some 4 or 5 years ago, and it's taken over the industry by storm. There are, if you've heard of Hadoop, Apache is sort of Hadoop 2.0 or successor to Hadoop-like systems. This is being run, so whenever you're using Facebook, when they're compiling profiles on you, etc., Apache is the machinery that, Spark is the machinery that runs in the background that can process large data sets over thousands of cores without you as a programmer having to know anything about that. You just tell it what you want to do with a certain piece of data, and it does all the distribution and so on. In our case, it can also handle streams. So we can write little Python programs that get each alert that comes in, decide that program can run a classifier on the alert and can do whatever it is that you're interested in, decide whether it's interesting for you, and pass it on or not. So you take all of that, and this is the kind of structure that you have. And George showed something like this. We're going to have a number of producers of alerts up here. And LSST is going to be generating an order of 10 million per night, but there are going to be others that are going to be, at similar orders of magnitude. And then we're going to have a number of brokers. These are going to be places where all these alerts are sent. And to you, these are going to be manifested as websites, basically. You're going to be able to access that website, get some kind of web page, and write your filter, write your query. These are the kinds of alerts that I want to get back. And once you do that, once you hit go, you'll start receiving a stream of alerts, or more accurately, your computer will be receiving a stream of alerts that match those queries. And then your challenge, your only challenge, quote unquote, would be to decide what to do with them. So here's a kind of a list of various things that the brokers are going to do. This is the simple filter that I showed. So virtually every broker is going to support something like this. But I think this is the more interesting case. You can build in much more advanced logic into those brokers. So something that takes full stream, that runs some, I said AI magic here because some of these things actually look like magic, but classifiers, supervised, unsupervised, that will tell you whether the object is of interest or not interesting, or not interesting to, I guess, the popular world, and therefore you're going to publish it in ANA or AppJ. Or if the project, or if the object is something that's really cool, like a merger of two neutron stars, or hypernova or whatnot, in which case you're going to publish it in Nature. And note that it can also be just wrong. And you're still going to publish it in Nature. How do we do this? That was the entire topic of the previous lecture, so I'm not going to go into any of this. This is challenging. This is the kind of thing that you're going to be worrying about. But But this is the only point I would like to make here. I think one of the challenges here is going to be to express everything in terms of what are called online algorithms. So what is an online algorithm? Wikipedia definition says in computer science, an online algorithm is one that can process its input piece by piece in a serial fashion, i.e. in the order that the input is fed into the algorithm, without having the entire input available at the start. Right? So what that means is, let's say I have 1,000 points, and I want to compute an average of the 1,000 points. I can take the 1,000 points and compute the average, and just sum them up, divide by n. Then I get 1,001st point. I can compute the average by taking all 1,001 points, summing them up, or dividing by n. Or I can do something smarter. I can take the previous average, just one number, multiply it by n, add the 1,001st point, and then divide by n plus 1. Right? The second algorithm here is the online implementation of the same thing. The difference is that, see, my first algorithm requires all the points to be available to the algorithm, which in a case of, say, an object that has 1,000 observations, it's a time series, it's a vector of 1,000 elements. Whereas if I express it in online terms, it's a vector of one new observation plus some state. And state, in the case of the mean, was just one number. So it's a dramatic reduction in the size that you have to keep around to keep updating your information about the object that you care about. So when we're thinking about classification, I think this is going to be one challenge. How do we come up with classification techniques? And there are many that already do this. But how do we come up with classification techniques that do not require all the information about the object to be present there all the time whenever we get a new point to update that classification? What we'd like to do is to have all that information somehow condensed into a much smaller state, and we can update it later. Bayesian methods, so anything that you can basically, that you can show that derives back to Bayes' theorem can be expressed in this way, because of Bayesian updating. So you can express everything as nu posterior equals likelihood times the prior, which was previous posterior. Good. So we're following this flow, and we've generated alerts. We've passed them through some filters. Finally, we go from, say, 10 million to perhaps 1,000 candidates that are potentially interesting to us, hopefully to an order of 10. And so what do we do now? So now we need to follow them up. And what I'm going to argue is we need a coordinated follow-up. So this is an image that I showed you at the beginning and shows an example of this with IPTF. So in the span of 12 hours, PTF detected the object, confirmed the object, an automated transient alert was sent. Then at around 4 hours after first observation, Keck got a spectrum, Swift was triggered, LCOGT was triggered, Swift got the observation, EVLA got triggered, LCOGT got the observation, Karma got triggered. The information was collected for this object in something like 12 hours. The reason why this was possible was because there was a coordinated follow-up network and a process in place for these kinds of objects. So that when an object appeared, you didn't have to think, what is it that I need to do next? You had a process. This is what I do. There's no time to now go and figure things out on the fly. Right? So the challenge now is that we want to do this, but for hundreds of objects each night. And not just us, well, actually it is us, but we have different science interests. So someone in my group may want to go follow up asteroids or something galactic. Somebody else may want to go follow up supernovae. And how do we coordinate all these demands for follow-up? I think that's going to be a very interesting question for the next 5 to 10 years. Because the vast majority of LSST discoveries will be faint. So 24.5 magnitude is the limit. And to follow up those kinds of objects, you're going to need telescopes with significant collecting area. But it will not be possible nor cost effective to, say, grab an ELT whenever they get built and point them to every single LSST detection. That, as I said here, that honor is going to be reserved for only the most interesting ones. So what you need to really be effective with LSST transients is a hierarchy of follow-up resources. So you want telescopes that span the range between what you have in LSST and eventually a 30-meter telescope. You're going to start with potentially thousands or hundreds of interesting candidates. You need to winnow that down to that one that you may really send to a really big telescope every couple of weeks. And for that, we don't have that many telescopes in the world, so we need some kind of organization. And so the example of that today, or the closest example of that today, is the Zwicky Transient Facility. So George already introduced it, so I'll just just summarize it here in one slide. So ZTF is a project run out of Caltech based on their ample experience with PTF and IPTF. It takes about 1,000 images per night. It has a 0.5 gigapixel camera. The camera actually has a 47 square degree field of view, which is quite impressive. With just 3 images, you can cover all of Orion. It detects 300 million sources per night, 1 billion objects it will see over a year, and it generates about 1 million alerts per night. So it's about a deci LSST, so 0.1 of LSST. And everything that I talked about alerts for LSST, we've actually built and it's running on ZTF. And this is literally the same technology. You clone on GitHub a repository that's been forked out of the LSST organization, and that's how this gets created. So we have ZTF data at the processing center at IPAC, the alerts in Avro via Kafka flow to 2 alert brokers or to 2 alert distribution point. One is at UW for our internal collaboration. One is on DigitalOcean, which is a cloud provider. That one supplies 4 different public brokers. And these public brokers then supply the community. So Antares is the public broker that the National Optical Observatory is running in Tucson, in Arizona. And I think it's going to become available for the next proposal cycle. Lesair is run out of Edinburgh and Queen's University Belfast. LCOGT has their own, and Alersa is a Chilean one. So we already have this kind of thing where 1 million alerts is streaming across the globe each night. Visualization is very important here, not just for science, but for operations. So these are the kinds of dashboards that I used to look at. I don't anymore because it turns out that this works. So we used to worry very much whether there are going to be kind of issues and breakdowns. But we started this system in June, and it hasn't had a single day of being down, the public system. So I'm kind of happy how this is working out. And it kind of makes sense because most of these tools we've taken over from the industry, and they really care about those kinds of details. So alerts pass through this system, and then the most interesting candidates end up on something called marshals. I didn't have time to talk about that, but in essence, once you winnow down from 1 million objects to an order of a couple of hundred, then you put them up on a web page, and then you ask the humans to help out, to look at them, to tag them with additional information, and to somehow rank order finally what should be observed with actual follow-up telescopes. And this is something that I think for LSST is going to be more difficult. I think we're going to need much more machine help before humans take over because they're going to be much more data. And once humans give the approval to start following up, we trigger this follow-up network chain. So P48, this is Palomar Mountain. P48 is the telescope where ZTF is. Candidates go to P60 to get a rough spectrum. If something is interesting, if one of the candidates turns out to match criteria that we care about, gets sent to P200, so that's the Palomar 200-inch, the 5-meter. Observations are taken there. If that, again, adds evidence that this is an interesting candidate, then all these other telescopes get triggered. So Keck, Gemini, Subaru have Apache Point, we have LCOGT follow-up, and so on and so on. So the kinds of things that show PTF, the kinds of things that I think are going to be needed for LSST, that's what ZTF is doing today. And the results are starting to come in. So here are just 2 examples. On the left side is a discovery of a potentially hazardous asteroid. These are objects that come uncomfortably close to Earth and can potentially collide over the next couple of millennia. And then on the right side, we have the first tidal disruption flare in ZTF. And ZTF actually has many more in the pipeline, but I'm not allowed to say how many until they're actually published. Turns out this is a very competitive field. Okay, so where do you find yourself in all of this? These alert streams look almost exactly like the LSST one is going to look, but they're still experimental and they're not open to the public. So right now we're just sending them to the alert brokers that will eventually make them open to the public. But we ourselves are trying to do something like that in 2019. So hopefully in the next 6 to 9 months, there actually is going to be an alert stream that anyone will be able to connect to. In the meantime, we have an archive of alerts. So if you want to see what it looks like, what an Avro packet looks like, or what that format looks like, then you can go to this URL, so ztf.uw.edu, and you will find fairly sizable tarballs of all these data. And the second thing you can do is, this is good for real science. This is 40% of all ZTF observations, and they're all public. So you can start constructing light curves out of this, look for interesting objects, and all kinds of science that the time domain enables you to look at. So that's already here. So I'll end with that, and I'll just put up this kind of a summary. So we're already in the era of time domain astronomy. It's not something that we have to wait for. That's already here. The increase in scale and complexity of the available data requires systems that, in essence, already exist in the industry. And it took some time for us to recognize that and to adopt them. But I think that part of the problem, in some sense, is now solved, or it has been solved for us. The greatest challenge going forward by far, I think, is classification, because we cannot ask humans to classify millions of objects in real time. Although I have ideas, you can do wonderful things if you gamify anything. If you get something like 100,000 users on a platform like Zooniverse and turn it into a good enough game, you might be able actually to pull it off and do real-time classification with LSST. And actually, real-time is better than not real-time, because you have studies in psychology that show that if there's a deadline, or if there's a fear of something going away, people will actually have a greater incentive to jump on it. So depending on how evil you want to be, you can construct a pretty good gamified version of a human alert filter. All right. I think that is still the greatest challenge. And the second one is to build coordinated follow-up networks. And the final note here is that you can already start practicing for this. LSST light alerts are already here, delivered by ZTF. We should have actual streams next year. But even now, you have the alerts that are this address. So I know this is a lot of kind of technical information. We wanted to split the two talks along those lines. But I hope this was useful and gives you a feel for what it takes to do these kinds of systems. It's not just algorithms and analysis. There's a lot of really engineering work behind it. And that's kind of what we're getting into as astronomy, as we're getting into this era of bigger and bigger science. All right, so thank you. Yeah, that's excellent timing. The only issue is the hemisphere. But it's close enough to the equator. Yeah. No, but those kinds of resources are going to be very, very, very useful.
Okay, more questions?
All right.